So once that's done, you would want to promote the RDS instance to your master and point your application to it. So a few best practices when migrating data. So like we discussed, it's best to take a backup from a replica or a slave if you can. And the obvious thing is to compress your backup so that the transfer to a staging server is quicker. So it's important to consider using a staging server in the import process, primarily because depending on the size of your data, it's possible that, like we discussed, it could take several hours to days for the import process to complete. So if you're using a process like MySQL dump, it's possible that due to network flappiness and failures, your process could halt, and you'll have to start it all over again. So you can control for that network-related aspect by uploading your files to an EC2 instance and then loading your data from there to an RDS instance. So you would want to use.
Why would you not just make the RDS instance a slave and then promote it? Why do the whole dump?
So you'll have to establish a baseline and load the data first, and then you can catch up the delta by setting up replication. So if you have to set up the whole thing through replication, you'll need to have all the bin logs from whenever you started the database, which is usually not the case. So you'll also want to use primary key sort order in order to make your data load process faster. So some of the things that you'd want to look at on the target side is use more hardware. So if you use a larger instance with more memory and more IOPS, the initial load process could be faster. So the good thing with our RDS is it allows vertical scaling up and down. So once you're complete with your load process, you can always scale down your instance to save costs. And you would want to disable multi-AZ. You would also want to disable binary logging. So these are really good best practices that you'd want to incorporate for production applications. However, while you're loading data, they don't really help much. So you would want to turn it off to reduce the amount of logging. And you would also want to look at a few MySQL parameters that can help you make this process faster. So InnoDB flush log at transaction commit is one. Auto commit is another. So setting these off will enable you to reduce the number of times transactions are written to the disk. This, of course, comes at a cost in that if your instance crashes or fails, you would lose some transactions. Again, you're dumping data, so it's not a huge risk. So you'd want to set unique checks and foreign key checks to 0 to speed up the process. And the last thing is InnoDB log file size. So this is something that was not editable using RDS in the past. We just made it editable for 5.6. By default, it's set at 128 MB. While you're importing data, you might want to set it to a larger value so that the checkpoint flushing is less frequent. Another important consideration is what input format you want to use. So you can use either a SQL input format or a flat file input format to load your data. MySQL dump, standard way, it generates a SQL file. You can also use MySQL dump to generate CSV files of each of your tables. So the MySQL dump essentially loads your schema and data at one go. All the constraints are taken care of. All the indexes are taken care of. You don't really have to do much when you're using MySQL dump in the standard way. However, if you're generating flat files, you would need to load your schema separately and then your data. So why would you really want to use flat files? So SQL execution could be slow. It's sequential. You could use flat files, especially if you use small files. The load process is faster. And you can also parallelize loading multiple files at the same time. So that helps. The other thing about MySQL dump, as we just talked about, is if the process fails, excuse me, so you'll have to start the process all over again. So if you have 2 days worth of work that has already been done, doing it again just seems very painful. So the flat file approach, you load files, each file as a single transaction. So if there's a failure, all that fails is that particular transaction. And as a database, if a transaction fails, it just rolls back. So you can just reapply the file from where you started having errors and continue as you go. So however, the SQL format is advisable for smaller databases. And the flat file approach is definitely something that you might want to consider for large databases. So once you're done with the initial load process, as we discussed, you would want to set replication from your master instance to an RDS instance. To set that up, you need to exactly know what binary log coordinates you need to use so that MySQL can start replication from that point onwards. So when you do a MySQL dump, it's possible to use an argument that will give you the binary log coordinates. So as you can see here, the MySQL dump output has master log file and master log position. So you would want to record that. And then you would want to set up a replication user on your master instance that can connect to the RDS instance. After that's done, you can set up the RDS instance as a slave to an external instance by using a stored procedure that RDS has. And arguments for that is a replication user that you just created in the previous step, as well as the binary log coordinates. And after that's done, you'll want to wait for your RDS instance to catch up. However, you will want to stop your application at some point so that you can catch up the residual transactions as well. And after the residual transactions are caught up, you can stop replication and then promote your RDS instance as a master by calling another RDS stored procedure. And after that is done, you can point your app to the RDS instance. You can also export data using the same process. However, you would just want to reverse the steps. You'll want to dump the data from the RDS instance, pipe it to your on-premises instance. This is possible through MySQL dump. And after that's done, you can set up the on-premise instance as a slave to your RDS instance and catch up the transactions made on the RDS instance thus far. One consideration here is RDS provides point-in-time recovery functionality and backs up transaction logs and takes them away from the instance and loads them into S3 every 5 minutes. So this means if your on-premises instance has not collected those transactions in that time frame, they might get moved away from the instance. So for that, you would want to execute another stored procedure and increase the bin log retention to a much larger value so that your on-premises instance can catch up. And the replication setup is only supported for MySQL 5.6. So another interesting thing that a lot of customers have asked is a way to sync their data from RDS to a Redshift instance. A lot of our customers use Redshift for their data warehousing purposes and RDS for their transactional data purposes. So we have recently released a functionality that enables you to set up, to change the bin log format from mixed, which is the default with RDS, to row. The row-based logging enables you to look at the change logs associated with the updates that have been made, and then you can make the same updates on your Redshift instance. So you can either apply the bin logs yourself, or you can use some of the AWS partner solutions from companies such as Unity and Flydata. So these solutions enable you to use a graphical user interface, set Redshift as a target, RDS as a source, and then they kind of take care of syncing the changes on the RDS instance and keep your Redshift instance up to date. So with that, best practices around data migration, we're going to look at some of the best practices around availability and disaster recovery. So as most of you know, RDS supports what we call as multi-AZ deployments. So multi-AZ deployments essentially create a physical synchronous replica in a different availability zone. The physical replication enables us to keep up with the load on the master. Unlike logical replication for MySQL, which is single-threaded, which means your replica could lag behind if there is a lot of load on your master instance. What happens when there is a failure? So we're going to go through the process and the steps that kind of happen behind the scenes when a multi-AZ instance fails over. The first part is we'll have to detect a failure, whether it's a networking level failure or a hardware level failure. You don't want to unnecessarily fail over very quickly, so we take some time to kind of confirm that the instance is indeed unreachable. And once the failure detection is complete, the standby instance is promoted to the primary. And this process takes about 5 seconds, typically. And after that is done, RDS communicates the change in the primary to your applications via DNS. So the CNAME is updated to point to the IP address of the secondary instance. And as long as you use CNAMEs to connect to the RDS instance, this process is kind of very seamless for you. Your application will have some downtime while the failover process is complete. And after the DNS update is done, your application just connects to the instance without you having to do anything behind the scenes. So after failover, or along with the failover, we also perform crash recovery on the secondary instance or newly promoted primary instance. So DNS update and crash recovery typically takes about 30 seconds. So in total, the failover time is ballpark 60 seconds on average. This could be higher if, for example, if you're using magnetic storage instead of GP2 or provisioned IOPS storage. So that tends to increase the crash recovery time, which could increase the total failover time. So this used to be 3 to 4 times last year. The failover time used to be 3 to 4 times this minute. Last year, our team worked very hard in kind of reducing the overall different phases that are part of the failover and reducing the time substantially. So after the failover is complete, your instance returns to the multi-AZ configuration. You'll have a secondary instance created behind the scenes for you. A lot of our customers also use read replicas for scaling their read-heavy workloads. So you can create a read replica to a multi-AZ instance, like here. You can use the read replicas to serve eventually consistent reads, and you can use your primary instance to still serve writes, to perform writes as well as serve consistent reads. You can also scale your read traffic by adding more replicas. And so what happens when a primary instance fails over? What happens to the replicas? So the replicas simply, so the standby instance or secondary gets promoted to the primary, and replicas simply connect to the primary instance and continue replicating. However, this is something that is not exactly the case with 5.1 and 5.5 because of a MySQL limitation. We're going to talk about that a little bit. However, the read replicas essentially can help you increase the availability as well while your instance is failing over, especially if you have a read-heavy workload, for example, a media website. So if you are using read replicas to serve your read traffic and you have architected your application in that way, your site will stay up to serve your read traffic. However, you won't be able to add new content until the failover happens. So this is another way to kind of increase your availability further using read replicas. So let's go back to the topic of 5.1 and 5.5. So with 5.1 and 5.5, it's possible that after a multi-AZ instance fails over, you might end up seeing errors like this with your replicas, with your application breaking. Client requested master to start replication from an impossible position. It's kind of a weird error. So this happens because of a MySQL parameter called sync bin log, and this is by default set to 0 in MySQL 5.1 and 5.5 with RDS. And what this essentially means is, even though MySQL writes to the bin log, it doesn't flush them to the disk and leaves it to the OS to flush the disk, as it would for any files. So what this means is, if your master fails over or performs a crash recovery, it's very likely that it's going to start a new binary log. However, your slave might still be stuck with the old binary log and the old position. So it will start to execute the old position, but it doesn't find anything. So that essentially ends up with this particular error. And one way to get around this error is to skip to the next master log. And RDS has a stored procedure through which you can do that. Another option is you can turn sync bin log to 1. However, with 5.1 and 5.5, there's a significant performance impact when you turn on sync bin log. So this is something that a lot of customers don't end up doing. So they live with the replication issues. With 5.6, the good news is sync bin log is turned to 1 by default by RDS. And it doesn't have, the reason why we did that is that it doesn't have as much of a performance hit as it had in 5.1 and 5.5. This is because 5.6 has binary log group commit, which essentially means commits across multiple transactions are kind of aggregated together and written to the disk. So this kind of helps with the performance. And MySQL 5.6 also has crash save slaves. That's a mouthful. So in 5.1 and 5.5, the replication coordinates used to be recorded in a MyISAM table, which is not crash safe. So 5.6, with 5.6, that kind of turned into an InnoDB table. So that kind of helps with replication reliability as well. So this is a chart that a benchmark from Oracle, which kind of shows that even with sync bin log 1, the difference between performance in 5.6 is not that much. So the red line and the blue line kind of shows you the performance difference when sync bin log equals 0 and 1 with MySQL 5.6. So you can also use read replicas for disaster recovery purposes, apart from scaling and availability improvement. So you can have standard multi-AZ instance and a multi-AZ application. You can use that for HA within a given region. You can create a cross-region replica in a different region for disaster recovery purposes. And some of our customers also use a cross-region read replica for read scaling and providing read locality. So for example, if one of your users travels from the West Coast to the East Coast, you might want to architect your application such that any data that they're reading is provided through a read replica, which is closest to the user. Of course, if a disaster strikes and the whole region gets affected, of course, this is something that is extremely rare and hasn't happened in the past several years. You can promote your standby instance to a primary and for business continuity purposes. Of course, the assumption here is you have a multi-region application as well so that you can get started in a different region if something were to happen to a given region. So let's talk a little bit about scale and performance after kind of going over the availability aspects. So we talked quite a bit about read replicas. So we're going to talk about an example through which you can use read replicas for read scaling. So let's take an example of a workload with 90% reads and 10% writes. And let's assume that most of the resources on your instance is consumed by this workload. So if you need to increase any of these dimensions, there's no room. So here, in this particular example, we created 4 read replicas and distributed the read traffic across them. So you can see that the write traffic, however, is kind of still getting replicated to the replicas. Even though your application writes only to your primary instance, it still has to get written to your replicas via the asynchronous replication process. So there isn't any write scaling here. However, you're able to scale reads, and you have a lot of room to grow. So you can scale further twice and still have some room left for this workload. You can scale 3 times, and you're kind of pretty much there. Another example is what if an application has more writes than the previous one? So 20% writes versus 10% writes in the previous case. You can still use the same approach, 4 replicas, and scale it 2 times. So here you're able to scale it twice as opposed to 3 times in the previous example. So here is a chart that kind of shows how much scaling you can get based on the write percentage of your workload as you increase the number of replicas. So you can see that the dark blue line at the top with 10% writes and 90% reads, you're able to scale it substantially as you add more replicas. However, the one with 50% writes and 50% reads, there isn't much scaling that you can get. Even if you add 32 replicas, you're barely getting 2 times as much scale. So of course, this essentially means if you have a read-heavy workload, you can scale it substantially by adding more replicas. So another interesting feature that we talked about in the beginning is InnoDB cache warming. So this is a native feature of MySQL 5.6. What it enables you to do is you can dump your buffer pool before a reboot, and then load it after a reboot is complete. So typically, when a reboot is done, you're starting from a cold cache. This particular functionality enables you to warm up your cache before you start hammering it. So dumping the buffer pool essentially doesn't dump all your pages. It just dumps your address space. It's not a very performance-intensive operation. Whereas loading the buffer pool will load the actual pages into memory. So there is a performance impact there. So our benchmarks have shown that turning on the buffer pool can help with, have helped with 4 times improvement in TPS on average for one of the workloads that we looked at. So here is an example of that workload. So it's 50% reads, 50% writes. So the purple line above is the one with cache warming turned on from the get-go. And then the yellow line is the one with unwarmed cache. So you can see that for about 9 minutes, there's a huge difference between the transactional throughputs of the instance with the cache warmed versus unwarmed. And the difference is about 4 times on average. So if you, especially in the beginning, the performance of the unwarmed cache instance is substantially lower compared to the warmed cache instance. So this is something that you can use to get better performance after reboots. And it's very simple to enable. All you have to do is turn on a couple of parameters, and MySQL takes care of the rest. So you can use a DB parameter group to turn on a couple of parameters, buffer pool dump at shutdown, buffer pool dump at startup. And the rest of the stuff is taken care of MySQL. The other, the thing to consider here, though, is the turning on those parameters only helps you with planned reboots with RDS. If your instance goes through an unplanned failover, which of course by default is unplanned, you won't be able to take advantage of this feature if you don't do anything. So however, we have a stored procedure that allows you to dump the buffer pool at your own chosen time frame. So we have an example here where we scheduled an event that dumps the buffer pool every hour. So what this means is if you have a failover after it has been dumped, say after 30 minutes after the dump happened, you'll still get your cache warmed up, but it's going to be 30 minutes stale. And the performance improvement may not be that high as you would get if you were dumping it more frequently. So I'm going to take a moment and let you savor this awesome piece of animation that I came up with. Thank you. So the next topic we're going to cover is schema changes. So as an application developer, if you leave me to it, I would perform schema changes every day to release new features. As people managing databases, I'm sure some of you in this room will tell me that it's just insane and extremely hard and painful to perform schema changes. So the reality is, of course, somewhere in between. So most of you, are likely dealing with it. So there are 3 main considerations while performing a schema change in terms of the options that you might want to use. You want to use an option that is fairly easy to use. You wouldn't want too much of a performance impact on your master instance as you perform the schema change. You would want it to complete fairly quickly. So there are 3 different options that you can use for performing schema changes with MySQL. The first one is using Read Replicas. We're going to talk a little bit about that. You can also use the native 5.6 functionality. So this is, again, a 5.6 feature that MySQL added. You can also use third-party tools like Percona. So using read replicas, you have a read replica. You can perform this operation on the read replica first. But before that, you'll have to turn that into a read-write instance. For that, you'll have to turn off a parameter called read-only. You can use database parameter groups for that. Once you're done with it, you can perform a schema change operation on your replica, say an alter table operation. After the operation is complete, which could take the time it takes, you could create a replica of it and promote your read replica to your master. The reason why you would want to create a replica is you want to preserve the state of the deployment as it were before the schema change, so creating it ahead helps. However, this whole process is easier said than done. There are a bunch of moving parts, and it's not easy because you could perform operations on the replica that could break the replication. So you'll have to be very careful in terms of what type of schema change operations you're performing and how that's impacting the replication stream. The native MySQL 5.6 feature, on the other hand, is very easy to use. It comes by default if you're using 5.6. And it's in place. And most of the operations don't block writes on your tables. However, it doesn't come for free. You still have some performance impact. MySQL still needs to organize data, even if you add a column within its table spaces. So it does impact the performance on your instance. It does allow you to write, but it has some performance implications. So MySQL 5.6 doesn't have any throttling mechanism for the amount of resources it takes up for performing the schema change operation, which means it could use a lot of resources that could actually adversely impact the performance on your instance. It could also increase the replica lag because replication is single-threaded, so replica will hold off replicating any other data until the schema change operation is done on the replica. So the time to complete, though, given there isn't much throttling on the resource consumption, is relatively less. The third option that we talked about is the Percona tool. So you can use something like pt-online-schema-change to perform a schema change operation on an RDS instance. However, you'll have to run it from an EC2 instance. You can install Percona on an EC2 instance or toolkit on an EC2 instance. You need Perl libraries for that. And then after that, you can connect to the RDS instance remotely and perform the schema change operation. This, of course, needs installation. It, however, has less performance impact because this particular tool considers the load on your master as well as the replication lag into consideration. And throttles the resource usage for the schema change operation accordingly. On the flip side, this means the operation could take longer. So here is a comparison between the Percona option and the native 5.6 option. So you can see that the performance kind of tanks for about 45 minutes or so while the schema change operation is in progress. On the Percona side, there isn't that kind of a performance impact. However, the Percona toolkit option takes about 1 hour 48 minutes, whereas the native option completes within 45 minutes. So if time to complete is important, you might want to consider the native option. So here is a quick comparison between all the three options. So ease of use, replicas is really difficult given the number of moving parts. 5.6 is the most easiest because it's just built in. In terms of performance impact, read replicas, of course, you're doing it on the read replica instance and not the master, so there's no performance impact whatsoever on the master while you perform this operation. So it's better if performance is the most important to you. And the native 5.6 option is kind of, relatively comes last. And time taken, the 5.6 option, completes reasonably quickly. However, the read replica option, the time taken probably is immaterial, given that it doesn't have any performance impact. So it's debatable which one kind of wins there. So these are the array of choices you can consider, and depending on what's important to you and for your use case, you can pick an option that works best. We're going to look at some of the new instance types that we launched, especially the T2 family, and how you can use that and GP2, the new storage type that we launched, to get better performance and get it at in a more cost-effective way. So GP2 storage, for those of you that do not know, is an SSD storage option. It provides 3 IOPS per GB base performance. And you can accumulate credits if you are using lower than the base. And you can burst up to 3,000 or more IOPS as you accumulate more credits. So T2 is a fairly similar story. However, it gives you credits in terms of compute cycles. And you can use those credits to burst the CPU usage as well. So one of my colleagues here performed a benchmark that compares the performance of these instances at different times of the credit usage. So as you can see here, the first couple of hours, a GP2 instance with a T2 instance with GP2 storage was able to yield 6,000 TPS. And after that, GP2 credits get exhausted, and you kind of fall to 3,800 TPS. And that kind of gets you for another 4 to 5 hours. And once the T2 CPU credits get exhausted, your overall performance drops to 2,200, which is kind of the baseline that you're going to get going forward. And you can also see how your credits are being exhausted using CloudWatch. So in this particular case, the orange line kind of displays the depletion of credits as time goes by. And once all of your credits are depleted, your CPU usage kind of drops, as seen in the graph. So how is all of this going to help you? So we've looked at a bunch of instance configurations and compared their price-performance ratios. So let's kind of go over it and see how it works. So we have an M1 medium instance with 200 GB of magnetic storage. Gives you ballpark 1,000 TPS and costs you 57 cents per hour. Now let's take an M3 medium instance. This is a newer instance family, costs less than the older generation instances. And here we have taken a provisioned IOPS storage type, 200 gigs, same storage, but it has 2,000 IOPS. And that kind of costs you 41 cents, which is cheaper, and gives you more transactions, probably twice as much. And then this is another instance configuration, an M3 large, which is a notch above the M3 medium, with the same provisioned IOPS storage. And this gives you, some more transactions per second, but at the same time, it also costs a little bit more. And this is interesting. So there's a T2 medium instance with 200 GB of GP2 storage instead of provisioned IOPS storage. So GP2 is significantly cheaper than provisioned IOPS. So as you can see here, it gives you much better performance than all the other options for 2 hours, for the first 2 hours in the day. And after that, it drops to a baseline performance of around, like 800 TPS. But the thing is, it costs you significantly less. It's 11 cents per hour approximately versus 58 and 52, 51 for the other options. So how is it going to help you? So if you have a workload that is bursty and requires high performance only for a period of day, and in this particular case, it's 2 hours, this can help you save costs significantly and achieve similar performance as the other options for your specific workload. Let's take another example. T2 medium, however, we have increased the amount of storage. So as we have looked at before, as you increase the amount of storage for GP2, it gives you more baseline IOPS. So 200 gigs gives you 600 baseline IOPS. 1 TB gives you 3,000 baseline IOPS. And this performs significantly better than any of the other options for not only just the first 2 hours, but for the first 18 hours. And then the credits gets exhausted, and it kind of gets to a baseline performance. However, the interesting thing to note here is the baseline performance is still better than a lot of other options. It kind of is close to the highest spec options that we have looked at, and it still costs you significantly low. So 23 cents versus 51 or 41 cents. So the gist of this essentially is the newer instance types, and the bursty instance types are an interesting family to look at. The GP2 storage is an interesting storage type to look at. You should strongly consider these two options and kind of figure out how they work for your workloads and how you can save costs. So that is all I have. We have about 7 minutes left. So if there are any questions, I'm happy to take them. Sorry, could you speak up? I think we don't have a mic here. To VPC? Yeah, so this has been an ask that we consistently hear from customers. So today you can do it through like a bunch of juggleries that you can implement through Read Replicas. We can talk offline. However, it's something that we are looking at and planning to support in the future. You can use snapshots too, but of course, I'm assuming you're talking about live migration to VPC.
How long does it take that, first of all, to recover its credits after it's dropped out?
To recover? Oh, so the question is, how long does it take for the T2 options to kind of recover after they've depleted the credits? So I think Grant.
So the way it works is that you get some credits back basically constantly, but it all depends on, if you go completely idle, you'll get it back. But in this example, like that final stretch, I think if you just kept pushing it that hard, it's never going to work again because it's using everything that it's getting. You'd have to go below that level. And so you imagine if you went to half, you start accumulating your credits back at 50%. It actually is on the detail page, it actually shows you the number of credits you get, and the maximum number of credits that can be held by each instance type. So you can look at the cloud metrics and really see how fast it goes back.
So, and of course, this is a benchmark. So, like we were pushing the instance to the brink. In a real-world workload, you probably, won't push it as much and kind of realize those credits as you go and pick up some performance after it drops to the base.
Do you know what I can look it up off the rhythm, how long it would have to be completely idle to get back up to 6,000 TPS? And it's in the dollars. Yeah, I'm not absolutely sure. That's what I want to say.
Any other questions? Go ahead.
Do you have any tips on speeding up the time it takes to launch a snapshot?
To launch a snapshot? To restore from a snapshot, you mean?
It takes like 15 to 30 minutes. Is there anything we can configure to speed up?
Do you?
Well, part of a snapshot is depending on storage type you're restoring to as well. If you're using magnetic, it's a little longer. It's basically do crash recovery depending on the snapshot. So if you're running magnetic, that's a little bit of time. Typically, like, I've seen snapshots come back in 5 minutes. But it depends on how much recovery and other things have to happen. So if something like GP2 is in that burst mode, what's one of the nice things for that, it'll come back a lot quicker because the fact that it bursts, if that recovery done, you get your instance back quicker.
One other question. So if you're not using SSD GP2 storage, how much is the gain? Is that the question? Have we looked at it?
I haven't done specific benchmarks. I mean, the BCDUs are listed for each of the instance types, but in general, you can get similar performance on the older instances. They just tend to cost more for what they provide. So it's mostly more about a price performance than it is really about performance.
Yeah. So in terms of compute, especially, if you look at R3 versus M2 instance families, the compute capacity is a lot more, and the cost is a lot less. So we haven't looked at the benchmarks per se, but the available compute capacity with the newer families is definitely higher. Any other questions? Yeah.
This is a little less related to the first stuff, but more like we ETL a lot of data overnight between RDS instance using Percona to not some percent of the time it's pretty stable, but occasionally we get these random communication errors.
Mm-hmm.
Is that just, is that like the bandwidth being filled, or is that, have you seen this often?
So you're writing from the RDS instance to an EC2 instance.
Well, yeah, we're moving data between
Sure.
the night.
And you end up running into communication issues. Are you using VPC?
No, they're all on the file, so it's RDS to EC2. RDS read replicas.
We probably take this one offline.
Yeah. Yeah. Any other questions, folks? Okay. Thanks for coming in, and please fill up the evaluation forms outside and help us improve for next year.